Let's begin with a beautiful image of the majestic Saturn and its sparkling rings. Ask yourself, why don't all planets have such gorgeous rings? The answer, as it often does, lies in the cold, hard laws of physics and the history of our solar system. So let's embark on a journey beyond the iconic realm of Saturn to understand what truly determines a planet's ring of fire. But before we start, if you're new here, make sure you hit that like and subscribe button down below to stay up to date on future videos. All right, let's get back to it. Before we dive into the mechanics of ring formation, there's something I want to point out. You might be thinking that rings should be fairly common in the universe. After all, when you see the likes of Saturn, Neptune, Jupiter, and even the Earth adorned with their unique rings, it seems like it could happen to any planet. But our solar system has a bit of a party trick up its sleeve. You see, more than 90% of the rings we know about, and yes, we have confirmed rings on more than a dozen other exoplanets, exist in systems with multiple stars. We just don't have as many eyes on those systems to confirm it. And with more than half of sun-like stars having at least one planet outside the habitable zone, the chances of finding gas giants with rings are pretty high. In fact, some studies suggest that if you take Jupiter and swap in a sun-like star instead, it would likely sport rings much like Saturn. So while Saturn's rings may seem ubiquitous thanks to our detailed view from Earth, the real cosmic rarities are the systems like ours where rings are much harder to come by. Now let's return to our solar system and explore the true story behind the formation of rings. When I say the formation of rings is brutal, I'm not exaggerating. These celestial adornments aren't born naturally. Instead, they're typically the shattered remains of moons or comets that ventured too close to their planets. To explain, we need to talk about the Roche limit. Imagine a comet zooming through the solar system. Its path takes it dangerously close to a gas giant. As the planet's gravity pulls on the comet, it stretches and deforms it. At a certain point, the gravitational forces exerted by the planet overcome the internal strength of the comet. Bang! It breaks apart. This catastrophic event leaves behind a ring of fragments orbiting the planet. But there's more to this story. Most rings we observe around planets are opaque, meaning we can see through them because they're relatively thin compared to the size of the planet. For example, Saturn's rings are only about 100 meters wide on average. If the fragmented comet or moon was massive enough, the resulting ring wouldn't be so thin. The Roche limit is named after the French scientist Edouard Roche, who calculated the distance from a planet at which a body will disintegrate due to tidal forces. For Jupiter, the Roche limit is roughly 9,480 kilometers. For Saturn, it's around 12,600 kilometers. And for Neptune, it's estimated to be between 5,000 and 14,000 kilometers. Any celestial body venturing closer gets ripped apart. Now, two main scenarios lead to collisions that form rings. The first involves fragments left over from the early stages of planet formation. As the planets formed from swirling dust and gas, there were bound to be leftovers. If any of these chunks came too close to a gas giant, bam! Disintegration and ring formation. Second, there are captured objects. Over time, comets or other small bodies from the Kuiper Belt or Oort cloud can get caught in a planet's gravitational pull and meet their demise at the Roche limit. Once formed, these rings are in a constant battle against dispersion. The particles that make them up are slowly but surely pulled into the planet or flung away. To persist, the particles must be held together by a delicate balance of forces. Enter the shepherd moons. These are small moons that orbit close to the rings, keeping the particles confined within a narrow band. Shepherd moons can also help keep the rings opaque by preventing the particles from crashing into each other and forming larger bodies. But even with these helpers, rings face another threat: orbital resonance. This happens when the gravitational pull of a planet or moon matches the orbital period of the ring particles. It's like a celestial dance, where the steps are repeated over and over again. Certain resonances can cause gaps or divisions in the rings. If the resonance is strong enough, it can break apart the rings altogether. For instance, Saturn's rings are famous for their gaps. The most prominent is the Cassini division, a 483-kilometer gap between two major rings. It's so wide that you could fit 10 Earths in line across it. This remarkable feature is thought to be maintained by the gravitational pull of a small moon named Pandora. But even without the drama of collisions and orbital mechanics, rings are still in a continuous struggle against the forces of space weathering. Solar wind, micrometeoroid impacts, and radiation constantly bombard the ring particles. All this cosmic punishment erodes them over time. Depending on the composition of the ring, this erosion can occur on timescales ranging from millions to billions of years. Now let's focus on the materials that make up these rings. They can be composed of various substances, including rock, dust, and ice. Most of the rings we observe are made of dust and ice, which makes them more susceptible to being swept clean by cosmic forces. Take Saturn's rings, for example. Its largest ring, the A ring, is mainly composed of water ice. Now imagine a micrometeoroid striking an icy particle in Saturn's rings. If the impact is forceful enough, the ice sublimates, meaning it transitions directly from a solid to a gas, leaving behind a trail of vapor and dust. Over millions of years, this process can cause entire sections of the rings to disappear. Compare this to Jupiter's rings, which are mostly made of rock. They're much more resilient to space weathering, allowing them to survive for billions of years. In fact, some of Jupiter's rings are thought to be remnants of a shattered moon called Himalaya. It was destroyed by tidal forces, but its rocky composition has allowed its ring to endure. Back to Saturn. Despite the dramatic story of how rings come to be, the grand spectacle we see today is actually a snapshot of a very brief moment in time. Some astronomers believe that under current conditions, Saturn's rings might only have been around for about 1 billion years, which is a mere blink of an eye in our solar system's history. The reason for their ephemeral existence is the same force that gives them their beauty, their thinness. You see, Saturn's iconic rings are a delicate balance of various factors coming together perfectly, and when the conditions change, they vanish. Now, it's crucial to remember that the presence or absence of rings doesn't necessarily indicate a planet's evolutionary stage. Some gas giants simply haven't experienced the catastrophic events necessary to form rings, while others may have had rings that disappeared over time. For instance, Uranus and Neptune, despite being similar in mass and composition to Saturn, sport only a smattering of rings. Scientists speculate that they haven't experienced the cataclysmic events needed to produce extensive rings. In summary, the formation and persistence of rings are a complex interplay of several factors. The size and mass of the planet, the composition and distribution of objects in the solar system, the gravitational influence of nearby bodies, and even the planet's magnetic field play key roles. It's like a celestial game of Jenga, where each factor is a block balancing the existence of these cosmic marvels. To wrap this up, let's go back to Saturn. Its mass is approximately 95 times that of Earth, giving its gravitational field strength about 11 times that of Earth's. If Saturn were less massive, its gravitational pull wouldn't be strong enough to hold on to the ring particles, causing them to disperse. On the other hand, if it were much more massive, the Roche limit would be further out, requiring more energy to break apart objects and form the rings in the first place. Also, Saturn's moon system plays a part in maintaining its rings. Moons like Pandora help keep the rings stable by confining the particles and preventing them from spreading too far. In essence, Saturn's mass and gravitational field strength, combined with its moon system, create the perfect conditions for ring formation and maintenance. It's a rare combination of circumstances that has allowed Saturn to acquire its stunning set of rings. And there you have it. The rarity of planetary rings, especially around sun-like stars, is a testament to the fleeting and almost miraculous nature of these cosmic wonders. They serve as a reminder that the vastness of space holds countless wonders that we're only beginning to understand. Until next time, keep looking up. and let your curiosity guide you through the cosmos.